Everyone, welcome back. So we're going to try out a combined gas vapor problem here. So you can see how you can combine a vapor cycle with our gas cycle. Now there's a lot of information. This is a very hard problem, so it's be a fairly long video there. But it will give you a really good introduction into how to do these problems. Okay, so what we have here, what are we dealing with? Well, combined gas steam power plant. Net power output of 330 megawatts, okay? I'm probably gonna make that red. Let's make that red. There we go. Pressure ratio of the gas turbine cycle is 11, okay, that's important. Air enters the compressor at 300 Kelvin and the turbine at 1100 Kelvin. The combustion gases leave the gas turbine are used to heat the steam at 5 megapascals to 350 degrees Celsius in a heat exchanger. The combustion gases leave the heat exchanger at 420 Kelvin. An open feedwater heater incorporated with the steam cycle operates at a pressure of 0.8 megapascals, okay? And the condenser pressure is 10 kilopascals. Whew, we have a lot here. And finally, we have isentropic efficiencies for the pump, for the compressor, and for the gas and steam turbines. Okay, this is an absolute ton of information. So the very first thing you want to do with this is just go ahead and draw your diagram so you have a little bit of an idea of what you're doing. So let's go ahead and do that. Let's make a TS diagram here. I'm going to try to make this fairly large. I can always put my work to the side. Here we go. TS. So let's do the steam cycle first. That's the one you might be the most familiar with since you're going through that right now if you're doing these problems in order. Okay, so your basic steam cycle looks something like this. You have a line here, that's the pump increasing the pressure. It goes up, we add heat in our boiler. It's now superheated, we come down, and then we go across. So that is the basic steam cycle. And for the most part, that's going to be pretty much the same. There is a slight difference here, okay? So I'm gonna get rid of this part right here and edit it. So what is that difference? Well, the first thing is we have an open feedwater heater, okay? The open feedwater heater means that at some point in my cycle, I'm taking my steam and I'm mixing it with my those liquid I have at the beginning to go ahead and preheat it, okay? To preheat it. So that's going to happen somewhere along this line. We're just going to pick a right line right here. As a note, this is not to scale, so forgive me if it's not perfect. And here it is. Okay, so this right here, that is where that open feedwater comes in. We have heat exiting through my condenser. We have heat entering through my gas cycle. I haven't drawn my gas cycle on here. Okay, so let's do one other thing. Second thing is it said was that the turbine for the gas and steam turbine was not 100% efficient, as in it was not perfectly isentropic. So the line I drew is for an isentropic turbine, so I'm going to have to bring this down, hopefully land in the middle there. There we go. That looks decent. Okay, and so I have that second line. Why do I have the second line? Because we're going to have to correct it. We're going to first do it saying it's isentropic, then we'll use its efficiency to figure out what it is. Now let's go ahead and number all this stuff. Number all this stuff so we have it here. Usually we start with our saturated liquid right there. Then we have going into the feedwater heater. Let's see, we added some heat to it. Then we increase the pressure. And after we increase the pressure, it goes into the boiler and gets some heat. Where does it get that heat from? It gets that heat from our vapor cycle. After that point, we are going to use that energy for something. And so part of the energy is going to go into our feedwater heater right here. And we'll have a second point, which we'll call 6S. That's if it was isentropic. And finally down here, this is when it's finished. And it's kind of repeating cycle. We got to the condenser finally. Okay, that looks pretty good. We give it all these numbers. Like there's a lot of numbers. There's a ton of numbers in this, okay? There's a ton of numbers. Now, I don't have to do this. I'm going to go ahead and draw my gas vapor cycle on top of this guy. I'm also going to make sure that it is missing it entirely. It doesn't have to do that temperature-wise, like it should be in line where it's supposed to be. It's just gonna make it very hard on me to do that. Though, I should do that for this. I'll just use a different color. We'll use a different color. We'll make this blue. Actually, that's not gonna be very different. We'll make it red, okay? Make it red. There we go. Okay, so right here, that was good. That's that line. We're going to go up straight. We're going to just draw our basic gas recycle or gas cycle. Go up here. We're going to come down and close it off. Okay, so that would be if I was perfectly isentropic both on my compressor and my turbine. I am not, and so for both of these, I'm going to have to go off to the side a little bit because I have to take into account those efficiencies. And so let's number these as well. So I was at 7, and so this point down here will be 8. Then we increase the pressure. This one right here will be 9, and this would be 9s. Didn't do a great job with making that the way it's supposed to be, so I'm going to redo that a little bit. There we go. If you ever wonder if your teacher make mistakes, we do, we totally do. Here's 11, 11s, that's 10, and I believe everything is now numbered, and also, yeah, heat goes in through here. Woof! That was a ton to do in there. So as we go along, I'll try to focus in on the different sections, zoom in a little bit for you. But you can see here, like drawing this cycle, there's a lot here. Why do I draw the cycle? I draw the cycles because you need to have some way of note keeping. Okay, now what is this problem actually asking for? Let's see here. Didn't actually put it in the problem statement. So the problem is asking for several things. The first thing it's asking for is what is the mass flow rate ratio of air to steam? So it's saying, what is the mass flow rate of air to the mass flow rate of steam? That's what we want to know. Now, how do we find that? Well, it's all from conservation of energy. The energy that is leaving the air is going into the steam, okay? So the energy that's leaving the air is going into the steam. And so I need to have that. I need to realize that. And so we're going to just look at our heat exchanger, okay? Magical heat exchanger guy. And so here's my magical heat exchanger. It's a box. And in this heat exchanger, I have one pipe that is air, and I have one pipe that is steam. They're very close to each other, and heat is going to go from the air into the steam and get it hot, okay? So you're like, okay, where is this happening in my diagrams? Well, we don't actually, we're not using any extra fuel to boil my steam. So right in here, I'm going to go ahead and I'm going to use a highlighter here just to try to make this a bit simpler. Right here, all that energy going into the water, that is coming from my gas, okay? All that energy is coming from my gas. And so the second question you're asking yourself is, okay, well, that's great. I see where the energy is going into the steam, but where is the energy coming from the air? Well, that's coming, let me go ahead and erase what I just wrote there. There you go. Energy comes along this path. Now, as a note, if you're wondering, at what temperature does this transfer stop happening? It happens when they're the same temperature. So if I look right here, this is the point where my steam, that's the lowest temperature of my steam. So, or I guess of my liquid or water at that point. So my gas can never get below that temperature. Okay, it can never get below that temperature. That's the lowest it can go. And so this would be 0.12 right here. So from this, I see two things. One, that the heat addition from 4 to 5, that's what's going into my steam. And two, the heat extraction from 11 to 12, that is what's going out of my air. And so I can connect those. Okay? So energy in is equal to energy out. Okay? That's what we have here. Energy in equals energy out, and that should be dots here. This is a steady flow device, so we don't have any change in energy for our system. And so I can choose this, however I want here. What I'm going to do is I'm going to say the outs are for the steam, the air going one direction and the steam going the other. And I can label these. So this would be 4 and that would be 5. For air entering and exiting, that would be 11 and that would be 12. Okay. So now let's figure out the energy. Does it have any kinetic energy? Does it have any potential energy? The answer is no, it has neither of those. So what we can do right here is I can go ahead and write my mass flow rate. So mass flow rate, I'm going to use S for steam, times H4, that's its enthalpy, plus mass flow rate of air times H11, that's the N, will be equal to what exits. So mass flow rate of steam times H5. My S's and 5's look almost identical. You know what I'm doing there though, that's okay. Probably should have changed it to a W. I'm going to keep it an S for steam. Or I wrote it. And then finally, what's exiting? Also the air, which would be the mass flow rate of the air times H12. Okay. So if I rearrange this, I can get my mass flow rate of air to steam equation. And it's based on the difference in those enthalpies. There we go. That would give it to me. Now, how do I actually get these? So this is a good question. Where do I start? There's so much information here. Well, you start with any point that you know completely. Okay? You start with any point that you know completely. As a note, let's see here. Can I erase the... I can't touch that. If I was going to pick a point, I would pick points that are not at the end of some isentropic relation, but at the beginning. Like right here and right here. Both of those points, I don't have to worry about doing any correction, so I can find them pretty quickly. Those would be good places to start. Maybe point 1, okay? That could be a good place to start. Just don't try to start at the end like at 7s or 7. You won't be able to have a good time there. That won't work very well. Okay, so which one am I going to start at? I'm probably going to start at point 8. I'm going to do the air first, and then I can use that to deal with water. Now, what does it tell me? Well, it says the air enters the compressor at 300 Kelvin. Okay, 300 Kelvin. As a note, we're going into an isentropic process out of that with some corrections, so we're going to need to go find some information. So let's do that. So we know that T8 is equal to 300 Kelvin. And so what we're going to do is we're going to go to the air tables. Now I already have these up for us. We don't have to worry about this too much. Let's go over here. And I'm going to find 300 Kelvin, which is right here on this line. So let's go ahead and get a screenshot. There it is. So here is 300 Kelvin. And I need its enthalpy, which is the first line. And I also need its absolute entropy, which is this line right here. Okay? So those are the two values I'm going to need. So I pull those out and I'll have what I need for the next steps. Now, why did I get the entropy? I got this because this is the beginning of an isentropic process. I'm going to be using that entropy to figure out the next points to get all the way around here. I need all this to be able to solve the problem. Okay, so back to my whiteboard. Here we go. And so what we just found is for 300 Kelvin, I have an enthalpy that's equal to 300.19. That's kilojoules per kilogram. My J did not come out at all. And I have an absolute entropy, that's why it has a little knot right there. That's equal to 1.70203. That's looking gorgeous. I like it. Okay. So what next? Well, we need to find our enthalpy. It's 0.9. and we can work our way from there. Now we're going to go ahead and find lots of these things. You're like, why don't we just find 11 and 12? We're trying to find this problem. Well, if we're going to do this, let's just go ahead and do all of it, because for other parts of the problem, like finding that workout, the thermal efficiency and other things, we're going to need all these values. So we'll just go in order, go wrap it around, and you'll get some good practice as we do it. Okay, so I want to find the enthalpy at all my points. So the enthalpy at point 9 is the one I want right now. However, this is at the end of a not isentropic relation. And so what I have to do is I first solve it pretending it's isentropic, and then I go back and I correct it. What's that corrected look like? Well, it's not that hard. So now we're moving on to point 9. This one right here was 8. Now we're going to go to 9. So if you're trying to correct the enthalpy, if you know it has some sort of isentropic efficiency, what you do is you say, okay, in a perfect world, how much energy would it have taken to do this? This is a compressor. In a turbine, it kind of reverses. But in a perfect world, how much work would it have taken to do this? And so I do that at the top. I say, okay, well, in a perfect world, it would have taken the isentropic amount minus wherever I am to get to this point. But we're not in a perfect world, so I have to take in on the bottom the real point I landed on minus where I started. Okay? So I'm trying to solve for H9. That is what I want. And so if I already know H8, sorry, the enthalpy 8, I just need to find out what my enthalpy would be after that isentropic process, and I can use this to rearrange and solve. I'll get something like this. So let's say H9 is equal to my enthalpy before the compressor plus the difference all over the efficiency. Okay, know most of that stuff, don't know this guy, so we gotta solve for this guy. And it's not that hard. It's not gonna be that hard. So let's go ahead and solve for it. How are we gonna do this? We're gonna find our absolute entropy, and then we're gonna go back to that table and see where that falls. So how do I find my absolute entropy afterwards? It's not that hard. So my absolute entropy after the compression is equal to my absolute entropy before compression plus my specific gas constant, natural log, and my ratio of pressures before and afterwards. At this point you're like, but Dr. Kidd, what is the ratio of pressures? It gave it to us. It gave it to us. Way up here at the top, it said pressure ratio was 11. Okay? That's what we're looking at. So we actually know that pretty easily. As for specific gas constant, 0.287. So I plug this in, I get S9 naught, it's going to be equal to, let's see here, make sure I write everything down properly. Yes, 1.70203 plus 0.287, natural log of 11. That looks good. And so what do we get then is our absolute entropy after the compression? Well, it comes out to be 2.39023. Really giving one of these decimal places today. That's kilojoules per kilogram Kelvin. So now what we're going to do is we're going to go back to our tables and we're going to find this. Where is this? What temperature? What temperature do I find this particular absolute entropy? So let's go look. Is it on the screen? No, it's not actually. I know where it is. I've already had this problem done, so I can kind of cheat a little bit. Let's see, went too far. Top of here, 2 columns, throw me off. There we go. Beautiful. Okay. And let's go ahead and screenshot. Capture full page. So I had 2.39023. And if you look right here, that's going to happen around this temperature, right? Now, it's slightly before that. So what we would need to do is actually interpolate. We have to interpolate to get the exact value for enthalpy. You can, with very, very high accuracy, because this is so close, just say, that's really, really close. If you're like less than 1% off, you can most likely just pick this and you'll still get the answer right. But if you want to do it completely correctly, you would need to interpolate between these two values to find the enthalpy that is also between those two values. I'm not going to do the interpolation right now. I already have it done, but you've seen in the past. If you need other examples of interpolation, I can post those as well. But by this point, I think you should be fairly good at interpolating. This is just a simple linear interpolation. Okay, so with that, I find that my enthalpy is somewhere between these two values. It's really close to this guy. It's just 595 rather than 596. And so what I get then is that H9, this is not with the S, we say this is isentropic, is equal to 595.83. That's if I interpolated. Okay, and that's going to be kilojoules per kilogram. So I have this guy, and so I need to now plug it in to here so that I can then find out what my enthalpy is actually. This is if it was isentropic. It wasn't isentropic, so I need to correct that. Okay, so let's see here. If I plug those numbers in, what I would get is that my enthalpy afterward is actually 660, let's see, yeah, 660.74. So you can see there's a big difference here. It took a lot more energy to get to the same state, okay? A lot more energy to do more or less the same thing. I don't want that. I don't want to have to use more energy to compress my fluid than necessary. That's wasted. But that gives us 0.9. Now, you're like, okay, so how do we get from 9 to 10? We don't really have to go from 9 to 10. Like I said at the beginning, any point that's at the very beginning of an isentropic process, not the end, is pretty easy to do. And it told us enough information. Like it said at the turbine, it's 1100 Kelvin. That's literally all I need. That's all I need for this point. So if I'm trying to find 0.10, I just need to look at my table for 1100 Kelvin. So we'll do that now. So T10, you're equal to 1100 Kelvin. Okay, we're going to go to the tables now. We're going to find 1100 Kelvin. And once again, because this is the beginning of an isentropic process, I'm going to have to get both the enthalpy and the absolute entropy. So I can find it at the beginning and the end, and then correct it using my turbine efficiency. Okay, so H10 right here, and S0 10. That looks good. We can do this, people. We can do this. And it's not on the screen, so I'm going to have to go ahead and scroll down to 1100. There we are. So I'm going to go ahead and pull it up for you so you can see it. Screenshot. It's right here. This is my enthalpy. And this right here is my absolute entropy. So I'm going to pull both those values out, and I can use those to solve for the next parts. So let's get back to it. There we are. So my enthalpy afterwards comes out to be 1,161.07 kilojoules per kilogram. And my absolute entropy is 3.07732 kilojoules per kilogram Kelvin. Okay, that one is easy. Now we move on to point 11. So where is point 11? Well, point 11 is after that isentropic process. So first, we're going to pretend like it's isentropic and find this point. Then we're going to correct to find this point. That's all we have to do. It's not going to be too terrible for this. And we're going to do it the exact same way we did last time, okay? That is it. We're going to do it the exact same way as we did last time. So first, we're going to find out our absolute entropy after this isentropic expansion. Sorry, well, after an isentropic expansion. So we're going to say, hey, S0 11 is equal to S0 10 plus our natural log. And you're like, what's my ratio of pressures? Well, it was 11 going up, and so it's 1 over 11 going down. It's 11th. Well, not 11th. Well, I guess it is 11th, yeah. 1 over 11 going down. That's just coming from the problem statement. So I plug in all my values here. So 3.077 plus 0.287, natural log of 1 over 11. And I would find that my absolute entropy afterwards comes out to be 2.389. Yeah. 2.38912 kilojoules per kilogram Kelvin. So with that, I can then use this to find my enthalpy afterwards, my isentropic enthalpy. So I'm going to find this in the table. So let's go back to the table and see if we can find it. And do I have the right number up? Oh, I'm so close, but no, I don't have the right number up. That's okay. So we're going to be looking at this fourth column. There we go. And I'm trying to find 2.39 roughly. And so it gets 570, I went 2.35, not quite there, go up to the top. And, oh, pretty nice, right about 590 I see it. That is pretty dang close. So once again, you would have to interpolate because this is not quite that value. And we're really close both times. But what I'm going to go ahead and say here is that if you didn't interpolate, the errors would be really, really small. So, vote your conscience there, people. Vote your conscience. Like the actual value is 595.19. This guy right here is 596. That is a very small difference between those two values. Okay. And I find that on the line with a temperature of 590. So I do that, and I go ahead and find from this that H11S, that's the isentropic path, is going to be equal to 595. This is, once again, if you had interpolated, I'm doing it based on interpolation because that's the right way to do it. But if you didn't do it, you're still going to have tiny errors, and most likely, you're not going to get it wrong. So that, though, is if I had it perfect. Once again, remember, we have a non-isentropic turbine. And so because it's not isentropic, I have to go ahead and correct this. So for a turbine, just in case you've forgotten, what you have to think to yourself is, well, how much energy should I have gotten out of this? That goes on the bottom because it's always bigger. Like, the bigger thing goes on the bottom for a turbine and also for a compressor as well. So how much energy should I have gotten out? Well, it's equal to the enthalpy before minus the enthalpy after an isentropic expansion. How much did I actually get out? Well, enthalpy before, that doesn't change, minus the enthalpy I actually got out. And so now what I can do is I can correct and solve for this. And so what I'll get is H11, you're equal to H10, enthalpy before, and I add in my turbine efficiency, that's good, times H10 minus H11S. That looks good. And when I plug in my numbers, I would get a value of 674.41 kilojoules per kilogram. Okay, we are doing great here so far. So the last point is point 12. Once again, like for this very first problem, I didn't have to do all this work. I could have simplified this somewhat, but I'm going ahead and calculating the enthalpies because you're going to need them later on for other parts of this problem, and so why not go ahead and get it done at the beginning. So looking back here, this is 12 exiting the heat exchanger and 11 that's entering it. So I need to figure out what this guy is. And you know what? That's really simple. Why? Because that's what the tip says. The gases leave the heat exchanger at 420 Kelvin. So the air, it leaves at 420 Kelvin. Okay? So I already know what its temperature is. That's all you needed. And so we have a really easy time finding that last one. This is a lot of work here. My goodness. So for 12, I know that my temperature is equal to 420. That's Kelvin. And so if I go to the tables, I'm going to skip it for this time because we've done there several times. I would find that my enthalpy at 420 would be equal to 421.26 kilojoules per kilogram. Okay, 421.26 kilojoules per kilogram. Okay, so that is all the air stuff done now. We've gotten all the air stuff. Now we've got to figure out all our information for steam. And once again, we're going to go through the whole process, even though we don't necessarily always need to do that, because we're going to need it for the rest of the problem. Even this particular part doesn't necessarily need it. So I've got to choose a point to, do all this. So let's go back to our view here and see what it looks like. Okay, let's see. If I was going to pick a point, I would probably pick number 1 right here. Number 1. Why? Because I know it's a saturated liquid, and I also already know the pressure. So that makes it really, really simple to me. It's a saturated liquid at that particular pressure. Really simple. And then after that, we're going to add the pump energy to it, and we'll start going from there. This looks, yeah, it looks fine. Okay, so what is the pressure for point 1? Well, going back to my much written over problem statement, let's see if I can find it. It's right here. 10 kilopascals. The condenser pressure is 10 kilopascals, both at the beginning and the end. So that's going to be very helpful. Also, our pumps are 100% efficient. That's really nice because I've got 2 of them, and I don't want to have to deal with that otherwise. So that looks good. So 10 kilopascals, let's go back down here and we'll start. Now, as a note, I've gone from the realm of air now to the realm of steam, okay? So this is all now steam. Don't forget that, because if you accidentally try to do everything for air at this point, 1, you're going to get really confused, and 2, you're not going to get the right answers. So, enthalpy 1, well, it's a saturated liquid, I know that, and I know its pressure. So I just knew it's a saturated liquid, that's just properties of a saturated liquid, and it's going to be at 10 kilopascals. So let's go ahead and jump over to our tables and see that. So we pop over again. Like, how are you already there? I went ahead and paused and got to the right table. I can do that, okay? I can do that. Now, well, I could just grab 1 value here. I'm going to go ahead and grab 2 because it's going to make things easier. We have 2 pumps because we have a, the open feedwater heater. And so I'm actually looking at this. What I'm going to do is I'm going to go ahead and grab the enthalpy for not just point 1, which is right here, because that's before 1 pump, but also point 3, which is before the 2nd pump. That's point 3 is after the feedwater heater. That's when the some of the steam has been used to heat the water. So I'm going to use both of those. And so that means I need 10 kilopascals for 1 and 0.8 megapascals for the other. I'm just looking at the enthalpy for 2 different pressures. Okay, we can do that pretty easily. Scrolling down here, pretty big problem. And so let's go ahead and do that too. Great. So first off, 10 kilopascals, easy to find, right here at the top. I'll go ahead and grab it just so you can have an easier time of seeing it. Here's 10 kilopascals. And I go over, I'm trying to find HF because it's a saturated liquid. And so that means it has an enthalpy of 191.81. 191.81. Okay, that's great. And then I go up to 800 kilopascals. You're like, wait, 800? It was 0.8 megapascals. Don't forget to convert. Otherwise, things go wonky. Now, usually you would notice for that, but just in case. And so doing it again. Let's see here. Here we are, 800 Kelvin. And I go way over. Let's see here, make sure I do this right. Specific volume, internal energy. Here it is. The enthalpy of a saturated liquid at 800 kilopascals. Oh, I said Kelvin earlier. Kilopascals, sorry, my bad. Okay, so I have both of those. I'm also going to actually need their specific volumes. Why? Because I'm going to be increasing the pressure, which will be right here. And so if I have both of those things, I can find out both the enthalpy before and after the pump, and I have the enthalpy and move on to the next parts of this problem. As a note, the amount of enthalpy that you add through a pump is really, really small. In many cases, you would just completely neglect it. I'm not going to in this case. I'm going to actually show you the steps, but you can actually neglect it. So, and usually get a very good answer. This one right here was 720.87 kilojoules per kilogram. That looks good. And its specific volume was 0.001115 meters cubed per kilogram. That looks good. And how about for enthalpy 1? Well, that was 191.81 kilojoules per kilogram. And its specific volume, I didn't really write it down nicely, it's going to be right here, is 0.00101. Does change, not all that much, but it does change. Okay, and so now we want to find the enthalpy that's put into the fluid by the pumps. That's not that crazy. My enthalpy after pump is simply equal to my enthalpy before the pump plus my specific volume times the change in pressure. So in this case, P2 minus P1. And I would have the same thing for after the second pump. There we go. Now we know all these pressures because they were given to us in the problem statement. And so this isn't too terrible. This one right here is 800. That one is 10. This one right here is 800 again, because it's still the same pressure. And then I also have the pressure at the highest point, which is 5,000 or 5 megapascals. Now I'm not going to write out all these numbers again because they've been written up earlier, but you just plug them in, and what I get in the end is that my enthalpy after that first pump is 192.6. So the pump added less than 1 kilojoule per kilogram. And for the second one, it's going to be equal to, let's see here, 725.5 kilojoules per kilogram. Kilojoules per kilogram. So that looks good over there. So you can see it's less than 1% in both cases. It's really small, but it is what it is. Okay. So what's the point next? We've got 1, 2, 3, and 4. Well, let's get point 5. That is after all the energy's been added. And that's the last point we're going to need in order to solve this problem. At least this first part. So I'm going to find this superheated point. As a note, we are not going to end at point 5. We're going to go ahead and find point 6 and 7, just so that we can have everything done for future parts. Now, how do I find this point? Well, it's really simple because it's given to you. It gives you the pressure, it also gives you the temperature. And that's enough to find it. But beyond just finding the enthalpy, we're going to need to define the entropy because we'll need that to find points 6 and 7. Okay, let's scroll way down here to get this. So H5, well, it's superheated. That tells us what table it's in. And we know that's for a pressure of 5 megapascals. It also tells us the top temperature, which was 350 degrees Celsius. So let's go ahead and find this. I want to find the enthalpy and the entropy. I'm going to go back to my tables. Let's scroll down to superheated. And I've got to find 5 megapascals. 0.3, 0.6, 1.2. I'm getting there, 3.5, getting closer. 5, here I am. Okay. Oh, well, that'll have to do. So 350 degrees Celsius gives me an enthalpy of, you can see right there. You can see my pointer at least. 2809.5, and that's 5 megapascals, correct? Yes, it is. Oh, I looked at internal energy, my bad. There you go. It's third column, not second. This is the enthalpy column right here. It is 3069.3. That's for 350 degrees Celsius. And the entropy is 6.45. I'll go ahead and show that to you just in case you're having trouble seeing my pointer. I do want to make sure that's easy to see. So right here and right here. That's for 350 degrees Celsius, which you could see if it didn't cut it off. And 5 megapascals. Okay, so that's enough information right now to solve this first problem. Like I have all my enthalpies for all 4 of those points. We're going to go ahead and calculate all of those so the next parts of this problem are just really simple and easy to do. So let's jump back to it and write those down. So enthalpy 5, what are you? You're 3069. 0.3 kilojoules per kilogram. And what's my entropy? My entropy is going to be equal to 6.4516. My pen is struggling now. Well, like my computer's probably struggling. Kilojoules per kilogram Kelvin. There we go. Not the best handwriting, but do what I can. Okay, so this then is followed by an isentropic process. So after that isentropic process, where am I? As a note, we're pretending it's isentropic to start. Well, where am I? I am no longer superheated. I'm going to be, well, I might be. It just depends on where this lands. So here's the question. I drew this and I show it as still being superheated. I very well may not actually be superheated. It's just one of those times where you have to kind of guess and check. How do you check? Well, you figure out what you would have if you check your entropy and you say, okay, is this too high for a saturated mixture? If it is, then you're superheated. If it's too low, or if it's within the range, you're a mixture. So we'll need to check that actually. We'll need to check that. We know our pressure. Pressure right here is 0.8 megapascals. So what we'll do to start is I'll go to the saturated mixture table and we'll go ahead and check at 8 megapascals is the entropy we had somewhere within this range. Because we're going to assume first that it's isentropic, so the entropy would stay constant. S6 would be equal to S5. Okay, so that was 0.5 right here. Now let's go ahead and do 0.6. So I know that pressure 6 is equal to 0.8 megapascals. And we're assuming for that first part that S6 is equal to S5. There we go. So let's jump back to the tables, check our saturated mixture table and see what it comes out to be. If that entropy that we had before, which was 6.45, is within the range of a saturated mixture, then I'm supposed to be a saturated mixture. Here we go, 800. Scroll all the way over. And so all I need to look at one value to know that I'm in the right table. I'll show you to you now. So my entropy was 6.45, and if I look over for 800 kilopascals, this is the row, go all the way over here, I see that for a saturated vapor it's 6.6616. So I'm less than that. I'm also more than for a saturated liquid, so this is the correct table. I'm in here. Which means if I want to find my enthalpy at this point for the perfectly isentropic process, we're not actually isentropic, I'm going to have to calculate quality. So I'll need SF right here, SFG, I'll need HF and HFG. And that will be enough to calculate. Remember, just when you're doing quality, it's just interpolation. That's all you're doing. It's just a fancy way of doing interpolation. So let's use those values and calculate my quality to start with and then my enthalpy afterwards. So here we are. So first off, my quality. So my quality for this point is going to be equal to my entropy at this point after the isentropic process minus the entropy of a saturated liquid all over the difference from a saturated liquid to a saturated vapor. Save time, I'm not going to plug those numbers in directly for you. I'm just going to show you the number at the end. And that'll come out to be 0.9545. Okay, now having that, I can then calculate my enthalpy at the end of this, imaginary isentropic process. So we'll do that again. So H6S is equal to the enthalpy of a saturated liquid plus the quality times the difference in enthalpy from a saturated liquid to a saturated vapor, also called the enthalpy of vaporization. And when I plug it in, what do I get? I get my enthalpy afterwards is going to be equal to 2,675.1 kilojoules per kilogram. Whew. We're getting there though. We're going to compost this. So with this one done, now we can go ahead and correct it. Now I have a turbine efficiency, which I'm going to use to do that. So the turbine efficiency is the same as last time. It's simply saying, okay, how much energy should I have gotten out? That should be bigger, so it goes on the bottom. And so that would be in this perfect case, And how much did I actually get out? Well, it wasn't that much. So I rearrange, and I get then that my enthalpy after the turbine is actually not as much as I thought it was. Or actually is more than I thought it was because I still have energy left in. There we go. And it comes out to be 2,730.3. I still have energy left in that flow that I wanted to get out, but I couldn't because it was not perfectly isentropic. Okay, we are coming to the end here. We have one more point to calculate. That's 0.7. Okay, this was just the beginning of my feedwater heater, and now I've got to go all the way down to the bottom of my condenser where I get rid of all the rest of the energy. And so this is very similar. So we're going to have a pressure here. The pressure in this case is 10 kilopascals. And my entropy, once again, I'm going to say, hey, S7, you're going to be equal to S5. And so using that, I can figure out where I am. So as a note, this one is most definitely a saturated mixture. I can go and look at that if I want to check it. To save a little bit on time, since we've already done that once, I'm not going to do it right here. You just take my word for it. And we can go ahead and calculate the quality and then the enthalpy using that. So my quality at this, magical, perfectly isentropic point, which we're not, but it's nice to dream, is equal to my entropy at the end. I don't know why I wrote 6 there, it should have been an S. Minus my entropy of a saturated liquid at that pressure, all over the difference between a saturated liquid and a saturated vapor. And it comes out to be a quality of about 0.7737. I can then use that to calculate my enthalpy at that endpoint. Once again, you're pulling all these values from the saturated mixture table at 10 kilopascals. And so this would be equal to my enthalpy way at the top, not at 0.6, but at the top. And let's see here. Oh, I'm looking at the wrong line there, my notes. Enthalpy of a saturated liquid at that pressure plus the quality times the enthalpy of vaporization at that pressure. And that comes out to be 2042.5 kilojoules per kilogram. Now, we have our enthalpy in the perfect scenario. We once again use our turbine efficiency to calculate what it would be afterwards. Once again, we want the biggest thing in the world for what gets energy out, and we don't have that, so that goes on the bottom. What do we actually have? Well, that goes on the top because that's less. Small thing goes on the top. If you get greater than 1 here, if you're trying to, if you plug the numbers in, it's harder when you're calculating for enthalpy. It's easier when you're calculating for the efficiency. But remember, the bigger value, the thing that should be bigger, goes on the bottom. And since my turbine in the perfect scenario would remove more energy, that goes in the bottom. The compressor, it takes less energy, so that goes on top. And which one is the perfect case is the one with the S in it. Okay, so I rearranged that because I'm trying to just calculate the enthalpy right here. And I get my enthalpy at 0.7 is equal to the enthalpy at 0.5 minus my turbine efficiency times that difference in the perfect scenario world. And I get my enthalpy to be 2,186.3 kilojoules per kilogram. Once again, you can see that I have some energy left in my flow that's then rejected as heat, and I don't want that. Okay, so this is enough. I now have everything we're going to need for the rest of the problems. So for us to solve this first problem, let's see, we need H5 and H4. We have H5 here. We have H4 here. And we had H11 and 11 and 12 from earlier. So those are the values I needed. I can take these and I can plug them up into my earlier equation way up here to solve for this mass flow ratio of these two. And so just giving you the values here, I would have 3,069, that's for H5, minus, let's see, 725, that's H4. I am rounding a little bit here, so getting you have some decimal points that I don't have here, that's why. Then for the air, that would be 674 minus 421. And that tells me then that I would need about 10 times as much air as steam to have this working. So I have 9.26 kilograms of air to kilograms of steam. Whew. Okay, that was a long first step. We did all the work we need for the next two parts of this problem. So let's go ahead and power through this real quick so we can get them done. Yeah, we'll go ahead and power through them. We'll power through them. It's like I can make a second video, but it's already long enough. We'll just go ahead and do this whole all in one gigantic video. I'd forgotten because it's been a while, why I haven't done all of this in a video before. It's because it takes a long time. Next, I'm probably going to make a PowerPoint for it. Well, you don't get to see me write things down. At the same time, it's a lot faster for me just to show you the numbers. Okay, so the second thing we want to find out is what is the rate of heat input into my combustion chamber, okay? So what is the rate of heat input into my combustion chamber to make all this work? So Qn, that goes into the air, and so that would be equal to the mass flow rate of the air times the difference in enthalpy from one side of the combustion chamber to the other. So that's H10 minus H9. And at this point, you're like, well, this is super easy. I already know the answer because we don't actually know the mass flow rate of the air. So we can't solve this right off the bat. We do know our enthalpies, that's taken care of. But how are we going to figure out the mass flow rate of the air? Oh, this is a bit more difficult here, isn't it? Yeah, it is. It is. But it's not impossible. We can still do this. So let's go ahead and get to it. Okay, so how am I going to find my mass flow rates? Well, that is going to come from my work. It told me that this was making 330 megajoules per second, or megawatts, okay? So my work is equal to 330 megawatts. And so since I know that, I can use that then to solve this. Okay, so my mass flow rate is going to be equal to, for air, is going to be equal to this power output over my net work. You're like, what do you mean by net work? Well, technically both the water and the air are making energy. Both of those making energy, so I have to take that into account. So let's go into what's actually producing power, this network. Okay. So this will be equal to the power output from the air. I should say net because we're using some to make it run again. Okay, work net air plus the work from the steam. Which isn't too bad. Now, one thing we need to think about here though is, like, you know, this is just a mass flow of air. How am I going to take this, connect that to everything else if I'm also have the steam helping out here? How do I know how much is steam in this equation and how much is air when it comes to my net work? Well, the way I do that is just remembering their mass flow rates. So if I'm actually doing the overall power, which I probably should have done to begin with, it's actually going to be written more like this. So it'll be the network of air times the mass flow rate of air plus the network of steam times the mass flow rate of steam. Now you're like, well, this doesn't look all that nice. How am I going to solve this? It's not too bad, actually. What I'm going to do is just pull a mass flow rate of air out of this whole side, divide the entire side by that, and what I get then is something that looks like the following. My power output is equal to work net, make sure I do this right, of air plus work net steam, mass flow rate of steam over the mass flow rate of air. And I also forgot to divide this guy by mass flow rate. There you go. And so this becomes my net work equation. And this right here, even though it's not poorly, it's not good handwriting, so my handwriting is better, my tablet is working a little bit nicer, is the ratio we calculated from earlier. We already know that ratio. And so if I can figure out how much work my steam and my air both produced, I can solve this. So, this isn't that hard to do. So let's go ahead and get done. We'll do air first because I did air first last time. There we go. So drawing my air diagram, it looks kind of like this. This is the compressor. That is the turbine. And we had different values. So this is 11 right here. That was 10. That was 9. And this one was 8. So the work going in is the difference between 8 and 9. And the work going out is the difference between 11 and 10. So I can find that pretty easily. The net work for my air is going to be equal to the difference in enthalpy from 11 to 10 minus the difference in enthalpy between 8 and 9, because I am using some of my energy to... Whoop! I always get my signs wrong. 10 is at the top, so I have to put it on the first one, otherwise I get a weird negative number here. There we go. Finally, 9 minus 8. So one's for my compressor, one is for my turbine. Okay, so if I do that, what I get is 126.12 kilojoules per kilogram. And now I have to do the same exact thing for steam. Steam's a little bit more difficult. Why is it more difficult? Well, it's more difficult because I actually am splitting my flow. Not all of it goes through the full turbine. Some of it is redirected into my open feedwater heater. So if I'm drawing my steam now, you have something like this. I'm just going to skip the fact that there's 2 turbines here. Goes up, over, up, down. Okay. So part of my flow is going here, and part of my flow is going here. And so I actually have to figure out how much work it made based on how much of that flow was redirected. So how do I figure that out? Well, it's not honestly too terrible. How? Well, we can just do it in terms of our conservation of energy. Okay. So let's make sure I have these names right. Actually, I don't want to go all the way up there. Yes. Okay. So this one right here was 6. That one is 7. This one right here is 3. That looks good. And I have, 2 right there for my very first. That should be fine. Oh, and 5 right here. Making sure I have the numbers right on my names. Don't want to mess everything up here. Okay. So, with that being said, let's think about what's entering and what's exiting. Okay, what's entering and what's exiting from my feedwater heater. So you can think about this as a big old box, okay? And one pipe, this is open feedwater heater, is just pouring in liquid water. Well, that is 0.2. A second pipe is pouring in a whole bunch of really hot vapor. I really wanted to draw a cloud there. There's my cloud. That would be from 0.6. And what comes out of here is that saturated liquid at 0.3. Okay, so what is entering here? Well, I have liquid water at 2, vapor at 6, and it's exiting as a saturated liquid at 0.3. So that's what's going in there. So let's just go ahead and write this in terms of our conservation energy. Energy in, well, mass flow rate 2 times enthalpy 2 plus mass flow rate 6 times enthalpy 6 is equal to mass flow rate 3 plus enthalpy 3. Okay, now think about the mass flow rates not in terms of an actual value now, but in terms of just fractions. 100% of what is in here goes out through number 3. Okay, so that's just 100%. We're not going to worry about the actual values right now, because in the end, they would all cancel out anyway. Well, how much is coming from the liquid side? Well, I can think about this in various ways. The liquid side, though, is the one that's producing the majority of my power. That's saying that I've gone all the way from 5 down to 0.7. This went through my condenser, okay? But some of that energy is lost because not all of it is producing power. I do take some of that fluid and I divert it at 0.6. So what we're going to do is we're going to say, hey, everything coming in from 2, you are the big fraction. I'm just going to call that y. And so whatever is left, so that's like 90% or 80% or 70% or 20%. It can be anything here. Actually, I completely did that. You know what? We'll go with it. We'll go with it for now. Now let's go mess with my numbers for later. Sorry. I should have done that for the steam. It's easier for numbers later, but this should be 1 minus y. Because in the end, it does make more sense for us to say how much was diverted from producing power rather than how much produced power. So that's how we'll do our fraction here. So this is my fraction that actually produced power, and then I have the fraction that didn't produce power. Letting my computer cool off for a little bit really did help. Note to self, people, let it cool down. My office is also ridiculously hot, so it makes it a bit harder on my computer. Okay, so what you can see here is I'm trying to find this fraction that actually got diverted, didn't produce any power. And I can now solve this because I know all these other values. So let's go ahead and do that. So I'm solving for y here. With a little bit of algebra, I would get something like this. So h3 minus h2 over h6 minus h2 is this value. When there's a 1 minus y here, that's why you see h2 twice. And so I get that there is 0.2082, so that's the fraction. So about 20%, 21% of my steam is extracted before it has the ability to produce all that power. So we already did our work for our gas. Let's go ahead and do our work for the steam. So my net work for the steam is going to be equal to, let's see here, the work of my turbine minus my pump work in. As a note, there was 2 pumps, so you have to do both of those. And so the work from the turbine is going to be equal to see, yeah, 769.8. Oh, I skipped a line on my thing. I was like, where is that coming from? I haven't given you that yet. Well, this we already calculated because we know the difference in enthalpies, but now I need to figure out actually how much power we produce from our turbine. That's the next thing here. So let's go ahead and do that. So for the work my turbine is producing for steam, that's going to be equal to my turbine efficiency, got to bring that in, times the difference from the top to the bottom, all till the steam is extracted, and then you remember you have some of it that makes it all the way through. So this is all the energy that was extracted before it gets diverted. That's 100% of my mass flow doing that. And then I do only a fraction of that afterwards, going the rest of the way down. That looks good. And so I plug those values in, I get a turbine work of 769.8. So that goes in here. Now how about the work of the pumps? Remember, work of pumps, the pumps are also only dealing with certain amounts of the flow. So we got to deal with that too. So my work of the pump, there are 2 of them, it's pump 1 and pump 2. And so let's see here. So pump 2, that's going to have all the flow because it's taking in, here, I'm going to draw my diagram here again. And do my best there, something like that. Okay, not perfect, but I did my best. This right here is pump 2. And so it has all my flow that's been diverted as well as all the flow that didn't get diverted. So it has 100% of the flow rate. And so that's a pretty easy one. What's the difference? Well, it's just the difference in enthalpy from one side to the other, which we saw was 4.68 kilojoules per kilogram. That's H3 or H4 minus H3. Trying to write that there, but my computer won't let me. And then I have the pump 1, which has only a part of the flow right here. And so it has everything that wasn't diverted going into pump 1. So I would add on to this 1 minus y, that's all the stuff that wasn't diverted. So roughly 79%. And then the work of that first pump, which is H2 minus H1. And the actual value for it was, let's see here, just 0.8 kilojoules. So this value is H2 minus H1. And so I get a very, very small value, which is that the work of my pump is, it's tiny. And I can bother even need the number. I was going to go ahead and do the math. So the net for my steam is going to come out to be at the end 764.5. Okay, so we have our steam, we have our air, we now know exactly how much we're producing, and so I can plug this back into my earlier equation to then solve for my net work in this case. So my net work is going to be equal to what I got for air, which is 126.12. Why do I have a, well, popped up randomly. Plus waters as well, which is going to be equal to 764. Remember, we have a whole lot more water flowing through there than air, or sorry, a whole lot more air than water, and so we're going to multiply this by that ratio, so making it similar. That looks good. And that gives me a network of 208. Just putting everything in per mass flow rate of air units. And so finally, I can calculate my mass flow rate of air using this. So that'll be equal to my work output, which is 330,000. kilojoules per second, all over the mass flow rate of air, which is, or sorry, the net work, which is 208.7. And that gives me a mass flow rate of 1,581.6 kilograms per second. And then I can finally plug this in here and get my heat produced, which is 791. That's a lot of energy going in. Wow. 791,146 kilojoules. Woo! Okay, the last thing it asks us is, what is my thermal efficiency? And as a note, this is really ridiculously simple once you get to this point, because your thermal efficiency, I'm just going to go this direction, make it easier myself, is simply equal to your work output over your heat input. And hey, what did I just calculate? My work output and my heat input. So that's going to be 330 megawatts over 791 kilowatts spin per second. So 91 megawatts. And it gives me a thermal efficiency of 41%. Didn't come out as a fraction, I just went ahead and turned it into a percentage. Okay, people. This problem was a crazy one. In the future, I'll probably try to put these in PowerPoint, unless you really like this. If you like seeing it written out, then I can continue to do it this way. Just longer videos. But thanks for watching. Hopefully this helps you, and I'll see you all next time. Bye-bye.